Good morning, good afternoon, everyone. My name is Arnaud, and I'll present you today a webinar on the new features in OpendTect 2.26. First, I'll show at the start of this webinar new features, improvements in the free part of the OpendTect system, namely the new HDF5 data format for wells and other various highlights. Thereafter, I'll spend the most part of this webinar on new features in OpendTect Pro and various enhancements. New features within the VDS data file handling with clouds and compression support, enhanced import-export for industry standard data formats, improvements within the Thalweg Tracker, and improvements within the support of shapefiles. Thereafter, we'll have a look at two major new features. One is the new fault tracker within the fault and fractures plugin, and another one is the zip model format within the OpendTect machine learning plugin. Finally, I also want to present you our redesigned installer for managing the OpendTect installations. Let me start with the new functionality in the free part of OpendTect. One of the largest new functionality is our new well data format. We have adapted the HDF5 file format to store all the well data in the project, which means that instead of having many files per well, we now have a single consolidated file for each well in the project database, and that is in H5 file. We have chosen that HDF5 format because it's a fast, multi-purpose, scalable container. It doesn't have any data loss. All the data can be natively stored in binary format, whereas previously some of the well data, specifically markers, but also in some cases logs, were still saved in text format. It allows us to have a separate metadata for each well part. Each log can have its metadata, each marker can have its metadata, and we can expand the storage for the well borehole information in a very easy way without having to create new file implementations. It is a cross-platform data format. It's portable, doesn't have any vendor locking. It supports API for reading and writing the data in Python, C, C++, Fortran, Java. It allows us within OpendTect to have a fast access to the well data in project with hundreds and thousands of wells. Besides, it will also allow us to store not only a single time depth model per well, but as many time depth models per well as we need. And eventually, it provides us more reliable means of updating and appending data to existing wells. Migration path for users is the following. Wells newly created in OpendTect 2.26 are going to be automatically created in that new format. Existing wells are not going to be automatically converted. They remain fully readable and writable in OpendTect 2.26. The copy option may be used to convert a well from legacy format to HDF5, and eventually OpendTect wells created in the new version of OpendTect will be readable in OpendTect 7.0.10, but they will not be writable. Let me present you other various improvements in free part of OpendTect 2.26. We have continued to improve our Python API to allow you to plug in your Python code without effort. So that mostly went into the ODBindy Python package and its companion C++ ODBindy library. We now have a full support of the 4K screens on all platforms. We have upgraded the code in the production database using the Proj 9.8 library. Now all HTTP connections are secure HTTPS connections using OpenSSL 3.5. And lastly, I also want to mention that we didn't forget about the developers. We have for them a full support of Visual Studio Code, Cursor, and Caro IDEs, and a full compliance to CMake 4. Let me now go to changes or enhancements inside OpendTect Pro 2.26. First, we've improved our support for the VDS data format to allow you to get a smoother visualization experience, including getting and using data stored natively in the cloud, AWS S3 on Azure blobs, using compressed or creating compressed VDS data files, and also using smart buffering technology by taking the leverage of the level of details, various level of details which may be present within the VDS data files. In the domain of import and export, we've added support for importing well data from landmark OWX, from importing sonar survey data for cavern visualization mostly. You can now import and export horizons and faults data using IESX data format. You can now import STL, AutoCAD, and GoCAD TSURF data formats, and also load 2D line geometry from SEGP1 data files. This window shows you the OWX import example. In terms of work for the user, not much else to do than selecting the input file. The software will digest the entire content of the file, give you a summary in the table that you see on the slide, and then as a user, you can QC this data, maybe even edit some of it before proceeding and actually creating the OpendTect wells from that OWX data content. We've made various changes, improvements in the well data manager. First, significant performance improvements, mostly but not entirely linked to switching to the new well data format. We have redesigned the right-click menu based on the cell, currently selected cell content. We have merged important functionality that was only available until now in the basic Well Manager. That functionality is now equally available in the advanced Well Manager as well. We have added support for custom mnemonics, so user can define custom mnemonics at the project level and then tag logs using these custom mnemonics. We have implemented a new regional marker manager, which is the tool we use to link the well tops with the 2D and 3D horizons. And that includes being able to very quickly assign regional markers to your well tops and to assign them to your seismic interpretations at the same time. And eventually we reworked the toolbar and the menu items arrangements in the advanced Well Manager. We have also improved a lot the support for ASCII import in OpendTect Pro. That starts with point sets and polygons, is going to be followed directly thereafter with fault stick sets, fault sets, horizons 2D and 3D. In all these cases, you'll have a unified import window where you'll be able to choose to import a single dataset from a single file, multiple datasets from separate files, or multiple datasets from a single file, which is what we use to call the bulk import tools. And for all these options, you can load CSV delimited data or space tab delimited data. The next changes I want to show today on OpendTect Pro 2.26 are within the Thalweg Tracker. So the Thalweg Tracker is a seed-based connectivity tracker, which is following the path of least resistance from the seismic data amplitude field. And we use it as a seismic facies tracker. How does it work? Well, the user is picking a seed, and then we'll evaluate at all neighbors the position of the voxel, which is most likely to match our seed location. So we iteratively grow the set of tracked seeds through the tracking mechanism of the Thalweg tracker, and the user specifies after how many seeds the tracking is going to be stopped. The main part of the window didn't change. In the dialog, the new additions are going to be found at the end after the tracking has been done. So we have had the two transparency sliders to quickly find seismic facies. Next to this, we have added attributes to better understand the deposition history and to find suitable seed positions for extracting 3D bodies. How does it work? Well, first you generate the Thalweg Tracker output, which is visualized in the usual way in the 3D scene. Here we have stopped after 1 million iterations for that Thalweg tracking. And then we use the transparency sliders in a very similar way as the horizon cube sliders by specifying a minimum and maximum value, either interactively or by positioning, by selecting a number. And based on the slider values, we only see a subset of the entire tracked output. So this is kind of the early stage of the tracking, the points which are the closest from the initial seed. They form this meandering feature we see very easily on the slide. If we go to later iterations, 80,000 to 150,000, we see a completely different jaw body emerging. If we continue going to even later stages of their iteration, we see yet another feature emerging from the Thalweg Tracker output. So these subsets can be saved as such in order to form jaw body. They can also be used to drop new seeds in order to retrack with more accuracy geologic features within these subsets. Based on that, we can also apply the new Thalweg attributes, which are displayed here. Iterations at the extreme, the distance skeleton, the relative distance, amplitude at extreme, distance, standard deviation, and the iteration at extreme. So here, these 1,000 cells from the new seed provide the end of this analysis. The last item I want to mention as an improvement in OpendTect Pro is our support for shapefiles. So as of now, we have a good support of the text labels within the shapefiles. They didn't appear previously except for their position. We have made enormous speed improvements in loading the very large shapefiles and rendering them. In 3D, the rendering speed is extremely fluid now. And we have also added an auto cropping of huge shapefiles based on the distance to the current survey. So if you have a shapefile which extends laterally over an enormous area, it's going to be cropped automatically. Finally, we have reworked the display properties to make them more dynamic, more contextually linked to the item being displayed from the shapefile, depending on whether it is a text label, a line, or a polygon. Within the Faults and Fractures plugin, the main new feature I want to mention in this webinar is the new interactive fault tracker. It is based on pre-processed fault net volume or any other AI discontinuity model volume you may have. And then interactively, we have as an interpreter to indicate which faults to track by placing seeds. It puts the interpreter in the center with assistance from the AI, which provides the input data. So as the interpreter will here set a couple of seeds on an inline, crossline, or Z-slice display and decide if we want to pick a single fault from the seeds or an entire fault set, in which case each seed is going to provide to be picked as a new fault 3D plane from the data and from the parameters that you can set as an interpreter. The tracking as such is done entirely in the background as a background task and visualized back into the 3D scene, where the tracking can then be further revised or the tracked planes can be further edited. Last new feature I want to mention is located in the machine learning plugin. It is a new container, the zip model, which has been introduced. It is a zip packaged ML model, machine learning model, which includes the trained model in its native framework format, PyTorch, for instance. It includes all the metadata to describe the model's purpose, input and output shapes, and the scaling. It includes the information required by the OpendTect machine learning plugin to use it as an input to run predictions. Each zip model contains structured metadata defined by the zip model info class that you can read, that you can digest from the DGBPy Python package. Mostly, and namely, you have to provide a platform type. Is the model a PyTorch model or is it a Keras TensorFlow model? You have to provide a learning type. To which workflow does this model apply? Does it apply to a seismic classification, to a log prediction, a seismic image-to-image regression? Is it a clustering? Which type of prediction are we doing? Are we doing a regression, supervised regression, a supervised classification, or an unsupervised segmentation? And what type of scaling was used in order to create that pre-trained model? So how was the input data normalized before it was fed into the model? That can be further extended with optional attributes like the name of the input channels, the output channel name, the shapes, so the size of the input of the various layers in the model, the data format, model name and platform version can also be specified in the zip model container. The zip model can also contain Python code in order to run the following operations prior to the training. It can be used to transpose the images. It can be used to calculate additional input attributes, which are not provided by the collection of the data, but which are calculated on the fly. You can use it to apply a specific custom-made scaling method. You can use it to apply basically any chain of pre-processing methods you would basically write in the Python code, which is sitting within the zip model container. It can also be used to run post-processing on the output image after the prediction was done, and obviously to undo the transposition. More detail will definitely follow in a dedicated webinar on that zip model data format. Finally, let me finish that webinar by presenting you the OpendTect installer, which has been largely reworked. New features include that you can specify if you want to provide and do a system installation of OpendTect or user-specific installation. And also the installation paths are going to be completely different between the community installation and commercial installation, leaving you the full possibility to not mix up community and commercial editions of the software. Also, if you have many different installations of OpendTect, the installer will give you a comprehensive overview of all the existing installations to facilitate their update and installation. In conclusions, OpendTect 2.26 is scheduled to be released at the end of this quarter. However, the macOS platform is going to be discontinued due to increasing complexity in keeping the software compatible, especially with the 3D visualization, and also in deploying it to the end users. Contributions from the users community are still welcome, however. Several new features which are presented in this webinar are going to be deployed and provided to you incrementally throughout the second part of the year. Do you have questions? Thank you for your assistance, and I'm now opening the floor to questions.